Hello everyone. Today we're going to learn about the ideal gas law. A quick review. Previously, we have covered 4 of the gas laws: Boyle's, Charles, Gay-Lussac, and the combined gas law. The 4 that we previously talked about were about how the properties of a gas sample will change as one or more of the others changes. A key assumption that was made for those 4 laws was that the number of particles, or moles, was constant in the sample. Since individual particles were challenging to count, we are going to use moles rather than just particles. The ideal gas law is built around the assumptions of ideal behavior for gases as described by kinetic molecular theory. For additional details about how gases are expected to behave under kinetic molecular theory, please see a previous video. The formula for the ideal gas law is P times V equals N times R times T. You will notice there are no variables that are changing. This law is simply about how the gas exists and what its properties should be based on what the others are. So let's talk about what each of these variables are. P is pressure, which is usually provided in atmospheres, although it could be in numerous other units. V is volume. V should be in liters in order to use this law. If it is not in liters, you should convert it before using this law. T is temperature, which, like it was for the other laws, is in Kelvin. And lowercase n is moles, which is our way of counting particles. R is the ideal gas constant. You will notice that R appears in other equations as well that we will talk about later on. R has different values depending upon what units are included. For example, the value for R, if atmospheres is involved, is 0.08206 liter atmospheres per mole Kelvin. Other values for R are provided on the screen here, for kilopascals, torr, and millimeters of mercury. When you are setting up an equation for the ideal gas law, you should pick the value for R who has the appropriate pressure units that you are using. For example, if you are using pressure in torr, you should select the value of 62.364 liter torrs per moles of Kelvin. So let's do an example calculation. A 2.34 mole sample of nitrogen gas occupies 5 liters at 300 Kelvin. What is the pressure in atmospheres for this sample? We know that we will be using the ideal gas law, Pivner. What are we solving for here? We are looking for pressure, which means we should be able to plug in the other variables. So let's plug in what we know. We don't know pressure. Volume we know is 5 liters, so that's what we will put in for volume. Moles is 2.34 moles, so we'll plug that in. For R, since we want our pressure in atmospheres, we should select the value of R that has atmosphere as part of its unit. So we will use the value 0.08206 liter atmospheres per mole Kelvin for R. Temperature is 300 Kelvin, so we will plug that in for temperature. Then we will simply use algebra to solve for P. The pressure for this sample would be 11.5 atmospheres, which is quite a high pressure. A quick notice. This law only works on ideal samples of gases, which would be those that follow kinetic molecular theory. Generally speaking, a real gas, one found in our real world, will behave most like an ideal gas when there is low pressure and high temperature. The idea here being that at low pressure, there is usually not very frequent collisions, and therefore less of a chance that there can be unusual pressures involved, or less of a chance that the IMFs could take effect. High temperature is also useful because at high temperature, particles are moving quite quickly. This means that they move away from collisions very quickly and also gives very little time for intermolecular forces to take effect. However, real gases do not always behave ideally. Sometimes a real gas will not behave ideally under the opposite conditions we previously described. High pressure and low temperature for a gas can cause it to behave in a non-ideal way. At high pressure, there usually corresponds to a small volume, which means particles are usually way too close together. This means individual volumes cannot be ignored. This also means that the particles might be able to have intermolecular forces take hold. Because the volumes are now too large to be ignored, this means that the recorded pressure is usually much higher than that predicted by kinetic molecular theory. Low temperature is also very bad for gases. At a low temperature, the particles begin to move much slower, which allows time for intermolecular forces to take effect, even though they are not supposed to really be present in this state. This means the particles begin to stick together, and therefore, because there are now fewer particles, there are less collisions. This leads to a much lower pressure than would be predicted by kinetic molecular theory. So please be careful. Ideal gases must follow the 5 principles of the kinetic molecular theory, and the ideal gas law only works on ideal samples.